In this video, we're going to be talking about linear transformations. So, linear transformations are a way to take a vector and turn it into another vector. And so, we can kind of define it as t goes from Rm, so a vector in Rm, to a vector in Rn. So, it could be R3, so it could be something like A, B, C gets converted to something in R2, and we just say like A plus B and C. So we're transforming this vector in 3 space to this vector in 2 space. So that's what transformation is. But to be linear, we have to fulfill 2 properties. So the first property is that the transformation of a vector plus another vector in that space has to equal the transformation of those vectors separately. So let's actually keep the order. So vector 1 plus vector 2. So this has to hold. If we took the transformation of t of 1 and so like 1 1 plus 2 4, and we got something like, let's say we're transforming it still into R2, so this is like R2 to R2. We got 2 2. When we take the transformation of 1 1 and the transformation of 2 4, we still better get 2 2. So that's all that this condition is really saying. So number 2, if we take the transformation with k times some vector in the space we're transforming from, it better be equal to the k times the transformation of just that vector. So if this this results in 3 3, t of v better just be 1 1, and then we can multiply 3 by 1 1 and get the same answer. So those are the 2 properties of so first we have that they have to hold under addition, and then number 2 that has to hold under multiplication. So let's give an example. So I think a really great example of this in practice is dot product. So let's think about let's say we have a transformation t of v that that multiplied, that was just v dotted with the vector 1 2 3. So this is a transformation from R1 R1 to, or R3, yeah, R3 to R1, because the result of the dot product is just a scalar. So let's say so what would have to hold is that T of, so let's define these two vectors right here. A is equal to A1, A2, A3, and B, so yeah, this is just an example. B is equal to B1, B2, and B3. So if we were to do the transformation of A plus B, we'd get so A plus B would just be this vector, where it would be A1 plus B1, A2 plus B2, A3 plus B3. Round that out a little bit. So when we dot this with this, we would just get A1 plus B1 plus 2 A2 plus B2 plus 3 A3 plus B3. And if we were to do T of just A, we would find that we would just get A1 plus 2A2 plus 3A3. And you'd see that for B, we would get the same thing. So T of B, we get B1 plus 2B2 plus 3B3. And you'd see that once we distributed this 2 and this 3, we would actually get the same things when we added, if we added T of A plus T of B. So it holds under that first property that we're talking about, the addition. Now we need to check number 2, does it hold under multiplication? So if this was to be true, T of KA would be equal to KA plus 1, or K1 plus 2KA2 plus 3KA3. So if we were to just do KT of A, so that's kind of like this example over here. So you can kind of see that this is pretty similar to this example over here. It would just be equal to K times all of this stuff, 1 plus 2A2 plus 3A3. So we would find that this in fact does equal these two transformations would result in the same thing. So I'll just distribute this real quick. Let's do this actually. 2ka2 plus 3ka3. So now that these are the same, the thing about linear transformations is every linear transformation has a matrix. So this is just super, super important. So the cool thing about linear transformations and how they're different from any old regular transformation is that a linear transformation has a matrix every single time. So what would be the matrix for a dot product? So this transformation, t of x equals x dotted with 1, 2, 3 can be represented by this matrix, just 1, 2, 3. And the reason that this works is that, so let's say we had some vector now, so this is just an example. So we had some, so now that we know that this transformation can be represented by this matrix, let's say we just had some regular old vector somewhere. Let's say it's 3, 1, 3. We could apply this transformation to it really quickly. So it would just be 1, 2, 3 times 3, 1, 3. And we see that this is a 1 by 3 matrix, and this is a 3 by 1 matrix. These terms match, so we can multiply them together. So we just get 3 plus 2 plus 9, which ends up being 14. So as a recap, this transformation was a transformation from R3 to R2, or to R1. So what this means is we took in a vector like 3, 1, 3, and just spit out a number, 14, which is in one dimension. So yeah, now you know about linear transformations and the properties that they have.